Hello everyone. In the previous video, we talked about qualitative behavior of linear systems when the eigenvalues are real and distinct. So now in this particular video, we are going to talk about case 2. We are going to consider the case where eigenvalues are complex, alpha plus minus j beta, where alpha and beta are real numbers. So let's say we have a system x dot is equal to ax. Okay. For now, I'm considering that A is 2 cross 2 matrix. Okay. And the eigenvalues are alpha plus j beta, alpha minus j beta. And the corresponding eigenvectors are v plus iw, v minus iw. Which implies that as per the definition of eigenvalues and eigenvector, A times eigenvector is equal to corresponding eigenvalues times eigenvector. So when you will multiply and you will rearrange, just compare the real part and imaginary part, you will get these two equations. Let's say M is a matrix with column V and W. So if you multiply both side by A, you will get this particular matrix AV, AW, and you can just put AV from here and AW from here. You will get this matrix. Now we can write this total, this whole matrix in terms of multiplication of these two matrices. You can write it down. This times this, you will get this element. And again, this times this, you will get this element. So these two are same. Now, if I multiply again M inverse here, M inverse means the inverse of this matrix. You just multiply here and we will get this final matrix, alpha beta minus beta alpha. So please note that alpha and beta are the real and imaginary part of the eigenvalue. So now let's transform like we did in the previous case. Z is equal to M inverse X. Okay. Now if I take the differentiation, I will get Z dot is equal to M inverse X dot, and X dot, as we know that X dot is AX, just put it here. And I will get this M inverse AM is equal to Z. Now we know that M inverse M is what? M inverse M is this matrix. So just put it here and just multiplying with this matrix times Z, you will get Z1 dot is equal to this and Z2 dot is equal to this. So you can clearly see that this is a, uh linear differential equation with cross terms. So it is not very easy to study this system. So what we can do is we can convert this system into polar coordinates. Yeah. So now the analysis of this system will be much easier. So now I'm going to show you how. Take Z1 is equal to R cos theta and Z2 is equal to R sin theta. Okay. Now just differentiate it. You will get Z1 dot is equal to this and Z2 dot is equal to this. Okay. R dot I already have. Okay, R dot for now we don't have R dot. We have this up to here only. Okay. After this, what we can do is that we can just solve these two equations and we will get this R dot is equal to alpha R, and similarly we will get theta dot is equal to minus beta. So we have these two equations. Just solve these two equations and we will get R dot and theta dot. Okay. Now r is what? R is the uh, distance and theta is the angle. Now the solution. So we can get the solution of this particular differential equation, and thus that solution is given by RT is equal to R naught e to the power alpha t. Similarly, the solution of this equation is theta t is equal to theta naught minus beta t. So now these two equations combinedly represent a spiral in Z1 Z2 plane. So this one is Z1 axis and this two is Z2 axis. This one is Z1, Z2, Z1 and Z2. Okay. Now please note that if alpha is less than 0, then this term will decay. And of course, if beta, I'm assuming that beta is greater than 0. I'm assuming beta is greater than 0 here for this particular uh, case. So if alpha is less than 0, this term will decay and theta is decreasing only. So this kind of picture will come. So let's say you start from here, the r is decreasing. What is r? R is basically the distance of each and every point on this trajectory with respect to origin. This is r. So this r is decreasing. You can clearly see, and the theta angle is decreasing in the negative direction because this term will get increasing only, right? I mean, this t will keep increasing. So this theta t will be decreasing. So this kind of picture will come. Now, if alpha is greater than 0, then this distance from the origin will increase. So see, you can clearly see that the distance from the origin is increasing. Yeah. And if alpha is exactly equal to 0, in that case, it will be simple r naught. So r naught means for all time t, the distance from the origin will be same. So this is the same. So it depends on the initial condition from where you are starting. You will remain there. Let's say if you are starting with r naught is equal to 1, so it will be a circle with radius 1. That is r naught. Let's say if you are starting with r naught is equal to 2, you will be on this circle with r naught is equal to 2. Yeah. It will not decay and it will not increase because alpha is 0. So I hope you understand. Now, such kind of behavior, if it's there, then we call stable focus. This kind of behavior we call unstable focus. Why are you calling unstable focus? Because it is keep increasing and going away from the origin. Because origin is the equilibrium point, right? And it is going away from the origin. So that's why it is unstable focus. This is a center. Why center? Because it is neither increasing nor decreasing. So this particular scenario, we call it center. Now, but we are interested in how the picture will look like in the actual coordinate frame. So the actual coordinate frame is x1 and x2, because I hope you can recall that this is a transferred coordinate frame. Not transferred, but um, we converted from x1, x2 to z1, z2, like here. So in the actual coordinate frame, u and v are the eigenvectors. So the picture will look like this. Now the trajectory will lie along the eigenvectors. That is the only difference. Yeah. So this is for a stable one, this is for unstable, this is for center. Okay. So this was all about this particular case. Let me know if you have any doubt. Please write in the comment box. Then I will try to answer your queries. Thank you.